So in this video, I'm going to introduce the idea of a density operator as a description of some subsystem of a quantum system, and then use that to prove the statement that I claimed in the last video, that we can always describe the state of a quantum subsystem using an ensemble. And so the idea is we have a quantum system and there's some subsystem A that we're interested in, and I'm just going to call B the rest of the system. And we introduce some basis labeled by little n for the states of A, and some basis labeled by capital N for the states of B. And then the general state of our entire system is going to be some linear combination of these combined basis elements. Okay, and now we're interested in how can we describe just the state of A. And so what I want to do is I want to think about any operator. So we'll let O be some operator that acts only on A. And so this could be some general physical observable that would be associated with the A subsystem. It's something that we could measure, and we could talk about the measurement probabilities for various outcomes, or we could talk about the expectation value for the operator O on the subsystem A. Okay. And so let's actually focus on that. The expectation value in this general state psi of O, which is just acting on the A subsystem, we can write that out using our general state here. And so then what we find if we write all of the basis elements explicitly, so that would be a sum over n and and m of CMM. So we're going to write the bra state there. So that would look like this, M tensor M, and then we have our operator, and then we'll write the ket state again using this formula. So now that's CNN, n cross n, and everything is summed over the indices. Okay, and now because O only acts on the first part of the system, we can rewrite all of that as this sum, and it's the sum over the same set of indices. So we have CMM star CNN, and then we have this matrix element of O between basis elements little m and little n in the first part of the system. And then we have the inner product between basis elements capital M and capital N in the subsystem B. Now these basis elements are defined to be orthonormal, and so this guy is going to vanish if M does not equal to N, and it's going to be equal to 1 if M is equal to N. And so then our entire sum simplifies. So we can write CM, and then we'll just set big M equals to big N. Sorry, this should be a little n. And then we have this matrix element OMN. Okay. And now I'm going to rewrite that further by defining a new object. So I'm going to rewrite this as just a sum over little m and little n of rho m n. Sorry, let's actually write it as rho n m times O m n. Okay, so I've defined this new object. It's going to be a matrix with elements that are given by this sum here, CMN, CM, star. Sorry, CN. Let's be careful and get the indices right. Okay, so basically I'm defining this set of quantities. We can think of those as being the elements of a matrix. And then you can just check that with that definition, this formula at the bottom reproduces the formula above it. But now we recognize the formula at the bottom as just the way that we would write the trace over this matrix row times the matrix that we get from these matrix elements of our operator. Okay. And so in the end, what we find is that you have the original expectation value of the operator O, which is acting on the A subsystem. It's equal to the trace of this matrix associated with the operator O multiplied by a new matrix, and we call the matrix row Mn, we call that the density matrix for the subsystem A. And the associated operator so that's associated with an operator that acts on the A subsystem. We could write that as rho equals rho Mn. Okay, so we could write that like this. That's called the density operator. Okay, so what's the deal here? This is an operator that acts on the A subsystem, or this density matrix is a matrix of numbers, which is D1 by D1. So it's just the size of that matrix is just related to the size of the A subsystem, and this object, it carries all of the information that we need to know in order to calculate any observables, to calculate any expectation values associated with our A subsystem. Okay, so if you know this matrix row, which you see is built from the data that defines the original state, okay, but it's not as much information because it's just let's say we have dimension D1 here and dimension D2 here. Okay, then remember originally we had D1 times D2 coefficients. Now this density matrix, that one just has, that's a matrix with D1 squared entries. And so for example, if D1 is equal to 2, if we're just talking about a single spin, and maybe D2 is really big, then it's a huge reduction in the amount of information just dealing with this density matrix as compared with dealing with a description of our full state. Okay, and we can see that just knowing the density matrix by basically this formula, just knowing the density matrix is enough to calculate the expectation value of our operator, which acts only on the A system. Okay, so we can see that the density matrix, or the density operator, gives a description of the quantum subsystem in the sense that that has all the information that we need. In the previous video, we talked about how an ensemble is the thing which describes the information about a subsystem. And now we want to relate these two objects. Okay, and so we notice that from the definition of rho, the trace is equal to 1, because if we take the trace of rho, that just gives the sum of the squares of all the coefficients in the original state, and that should sum up to 1. And furthermore, it's not hard to show that all of the eigenvalues of this operator have to be positive. Okay, so this is a special kind of matrix. It's Hermitian, trace 1, and all the eigenvalues are positive. All of those things are straightforward to show from the definition. And so that means that if we now think about this operator, we can find some set of eigenstates which are orthonormal, okay, and which have some positive eigenvalues. Okay, so let's do that. Let's let pi and psi I be the eigenvalues and eigenvectors of this matrix rho, or this operator rho. Okay, then the fact that the trace of rho equals 1 means that the sum of the eigenvalues is equal to 1. And so those have interpretations. We can, if we want, interpret those as probabilities. And so the final thing then is to notice that if we write out this expression, which was the expression for our expectation value, then we can describe that in terms of these eigenvalues and eigenvectors. And so the way to do that is to think about now going to the basis where the density matrix rho is diagonal. Okay, so in that basis, we can easily evaluate this trace, and it's going to be equal to this expression, which is the sum over I of the probability pi, so that's one of the eigenvalues of rho, times this matrix element psi I, O psi I. And that's exactly the expression that we had before when we were talking about ensembles. And so that actually proves this previous statement. So that shows that the ensemble pi and psi I describes our state, describes the state of the subsystem A. Okay, so let's just summarize. We started with a state of a two-part system. We defined an object called the density matrix associated with the subsystem A. We said that object is a Hermitian matrix with trace 1 and positive eigenvalues. And so from that information, we defined this ensemble to be the collection of the eigenvectors of that matrix, or the eigenstates of that operator, together with the associated eigenvalues. Okay, so that has the properties of an ensemble. And then we, through our derivation, we realized that the ensemble average of any observable acting on the subsystem A is going to be equal to the expectation value of that observable in our original state. Okay, and so that proves that this ensemble that we defined through calculating this density matrix, it faithfully captures all of the properties of the subsystem A. And actually, one thing that I didn't mention in the previous video that's clear from this derivation is that when we have a subsystem that defines, when we have an ensemble that defines a subsystem, we can take the states in the ensemble to be orthonormal states, because in the way that we derived this, those were going to be eigenstates of a Hermitian operator. And we remember that we can always take those to be orthonormal.